Okay, hello everyone. Today we will learn the continuous random variable number 6, and this will be the last lecture for the continuous random variables. Okay, chapter 4.10 is about Chebyshev's theorem, and theorem 4.11, the Chebyshev theorem is like this. Let y be a random variable with finite mean mu and variance sigma square. Then for any k larger than 0, these equations hold. And actually, we already proved this for the discrete case, and um, the proof that I used was the generalized version of the proof, and um, so the proof is the same. And actually, in the book, they also have their version of the proof for theorem 4.13. So if you are interested, you can read by yourself for the proof. Um, and so I will move on. Okay, let's move on to example 4.17. Suppose that experience has shown that the length of time y required to conduct a periodic maintenance check on a dictating machine follows a gamma distribution with alpha 3.1 and beta 2. Okay, for the length of time y required to the maintenance check for a machine, that it follows gamma distribution. So y follows gamma 3.1 and 2, and a new maintenance worker takes 22.5 minutes to check the machine. Does this length of time to perform a maintenance check disagree with prior experience? So, so the time of these, is that normal or abnormal, uh, given the prior experience, which is if you calculate the probability of y is greater than or equal to 22.5, then probably you can mention that this agree with the prior knowledge or not. So to do that, probably we can calculate this thing, probability of um, uh, absolute value of y minus mu divided by sigma is greater than or equal to k, which is less than or equal to k squared. So so we can you can calculate this number, and so uh, to set this, probably we can use set 22.5 is equal to k, mu plus k sigma. So to do that, probably we may need to calculate mu and sigma. So EY is for the gamma distribution, EY is alpha beta, and VY is alpha square beta. So you can calculate the sigma is alpha square root beta, mu is alpha beta. So from here, you can calculate this thing. Probability of y is greater than or equal to 22.5, or y equals less than or equal to um, uh, mu minus k sigma. Okay. Uh, so you can calculate mu and sigma with the formula, and if you put mu and sigma here, then you will calculate this is less than or equal to k square, and actually the probability of this thing, probability of y is uh, greater 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 than or equal to 22.5 um, is less than or equal to this, because here probability of y is greater than or equal to 22.5. This the probability for this event is less than or equal to probability of y is this event and this event. So this one is smaller than this one, and this one is smaller than k squared. And so if you solve this for k, then you can calculate the probability of y is greater than or equal to 22.5 is less than or equal to k squared. And so you can decide whether this probability is rare or this probability is large. If this probability is rare, then you can say that the performance of new maintenance worker is significantly different with the prior knowledge, prior worker. We can conclude something like that. Okay, thank you. Here are homework for 4.10. The chapter 4.11 is about expectations of discontinuous functions and mixed probability distributions. So, what this means is that distribution functions that are partly continuous and partly discrete. So in previous lectures, we learned about distribution functions fx. When we have discrete random variable in the form of fx, it is a step function, and it reached to 1. And if the random variable y is continuous distribution, then it is the continuous function, something like this. So when random variable y is discrete, it looks like step function. For the continuous random variable, the distribution function is continuous function. However, what about we have mixed probability distributions? Like there's a point mass, and also it have um, so 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 it contains partly continuous and partly discrete. What it means that something like this, partly continuous, but at the it's increasing function. So yeah, partly continuous and partly discrete. So here's step function part, and it reached to 1. So this is the function that we will cover this chapter. Um, So there are two cases for this. A random variable gy that is discontinuous function of a discrete or continuous random variable y. For a discrete or continuous random variable of y, gy, a new random variable gy is again random variable. However, if the function g is a discontinuous function, then it could be generate the mixed probability distribution. Okay, this is the first case. And the second case is that random variable of interest itself may have a distribution function that is continuous over some intervals and such that some isolated points have positive probabilities. So there's two cases um, for these mixed probability distributions. Let's check from the next slide. And the example 4.18 is in the first category, a random variable g of y that is a discontinuous function of a discrete or continuous random variable y. Let's look at the example. A retailer for petroleum product sells a random amount y each day. Suppose that y measured in thousands of gallons, has the probability density function of this. So the amount, so it is the density function is defined on 0 to 2, so which is 2,000 gallons, 2,000 gallons. Okay, and the distribution looks like this. So this is model for the amount of gallon for sale, and the retailer's profit turns out to be $100 for each 1,000 gallons sold if y is less than or equal to 1, and 40% extra per 1,000 gallons if y is greater than 1. Find the retailer's expected profit for any given day. So here, the new profit, which is g of y, is 100 times y if y is less than or equal to 1, and it is 140 y if y is greater than or equal to 1. Okay, so find the retailer's expected profit for any given day, which is we want to calculate expected value of g of y, and actually this is integrating from 0 to 2 g y fy dy by definition of the expectation, and for here gy is defined as 100y or 140y from different intervals of y. So this is 0 to 1, 100y fy, which is 3 over 8 y square dy plus from 1 to 2, it is 140y times 3 over 8 y square dy. Okay, I will leave the calculations to you. So if you solve these two integrations and sum them up, you will get the answer for this question. Okay, so this is the first type, a random variable gy that is discontinuous function of a discrete or continuous random variable y. Okay. Next, we will talk about the second case, which is mixed probability distributions. So a random variable y that has sum of each probability at discrete point, sum of each probability mass on discrete point, which is discrete random variable case, and the remainder spread over intervals is said to have a mixed distribution. And here, the remainder spread over intervals, which is the case for continuous random variable. And so the situation is kind of mixed. The in the random variable we have discrete cases and also continuous cases. So, and in this case you can specify your distribution function like this. Here f1y is the step distribution function for discrete random variable, and f2y is a distribution function for continuous case. And C1 and C2 are the accumulated probabilities for so C1 plus C2 is 1. Okay. Let's move on to example 4.19. Let Y denote the length of life of electronic components. These components frequently fail immediately upon insertion into a system. It has been observed that the probability of immediate failure is 1 over 4. So this immediate failure always happens at the insertion time. This is probability mass, which is discrete event, and the if a component does not fail immediately, the distribution for its length of life has the exponential distribution function of this. So so for the event at immediate insertion, there's a probability mass of 1 over 4, and and if it passes this the probability with probability of 3 over 4, the following event follows exponential distribution of this. So the problem is find the distribution function of for y and evaluate p of y is greater than 10. Okay, so this is mixed probability distribution, and so we can specify Fy as C1 F1y plus C2 F2y, and the F1y, we have point mass at point 0, so our F1y it's something like this. Until y equals 0, it's 0, and at point 0, it have probability to 1, jump to 1. So this is our f1y, and our c1, c1 is immediate failure, probability of immediate failure, which is 1 over 4. If c1 is 1 over 4, then c2 is 3 over 4. So the probability for the discrete event is 1 over 4, and probability for the continuous component is 3 over 4. And the distribution function for the discrete case, the point mass is point mass is on the y equals 0. Every point mass is accumulated at y equals 0. So we have step function like this for f1y, and for f2y we can calculate the f2y, which is probability of y is less than or equal to y, which is from 0 to y, e to the minus y dy, and this is e to the minus y minus e to the minus y 0 y, and this is minus e to minus y plus 0 1. So okay, so this is our f2y. So the shape of f2y is something like this. At point 0, we have 0, and this approaches to 1. 1. As y goes to infinity, it approaches to 1, so it looks like this. Okay, and so the distribution function fy is uh, it is 0 if y is less than 0, and if y is greater than 0, it have point mass so uh, 1 over 4. f1y is 1 over 4 if y is greater than 0, plus it is 1 minus e to the minus y times 1 over 3 over 4 if y is greater than 0. Okay, and so the shape of the fy would look like 0 until 0, and there's jump of 1 over 4, 1 over 4, and it goes to 1, something like this. That's our distribution function, and p of y is greater than 10, which is 1 minus fy, which is, we can put 10 here, so 1 minus, we put here, which is 1 over 4 plus 3 over 4, 1 minus e to the minus 10, and then you will find the answer for this question. Okay. Okay, let's move on to definition 4.15, which is about this expected value of mixed distribution. So let y have the mixed distribution function. So fy is what is mixed distribution? With it is fy can be written as c1 times f1y plus c2 times f2y, and here c1 plus c2 equals to 1, and the f1y is distribution function for discrete random variable, and f2y is distribution function for continuous random variable. So here the x1 is discrete random variable with distribution function f1y, and x2 is a continuous random variable with distribution f2y, and let gy denote a function of y. Then expected value of g of y can be written as c1 times expected value of g of x1 plus c2 times expected value of g of x2. Okay, let's try example 4.20 to understand what it means. So for example 4.20, find the mean and variance of the random variable defined in example 4.19. In example 4.19, we have point mass at y equals 0. So f of y, in the previous example, f of y is 0 when y is less than 0, and 1 over 4 plus 3 over 4 times 1 minus e to the minus y when y is greater than 0. And the shape is here's 1 over 4, and it starts from here and approaching to 1. So this is distribution function for y. And here, the x1, what are x1 and x2? X1 is discrete in case. For x1 have point mass at time 0. So probability of x1 equals 0. It is 1 for discrete case. The probability is this thing. And what about x2? X2 is the geometric distribution. exponential distribution. So exponential distribution with lambda equals 1. And the y, the new variable y is 1 over 4 times x1 plus 3 over 4 times x2. Okay, so this is our new mixed distribution. Okay, and here, what are expected value of x1? It is sum of when x1 equals 0, the probability of x1 equals 0 is 1, so which is 0. And what about expected value of x1 squared? And actually, this is again um, 0 squared, which is 0. 0 squared times 1 equals 0. And what about this one, expected value of x2? For the exponential distribution, it is lambda, which is 1. Expected value of and variance of x2, it is also lambda 1. And so expected value of x2 squared is variance of um, x2, which is e of x2 squared minus ex2 squared. So which is 1, this is 1, so this one is 2. Okay, and with the definition here, we want to find mean and variance of the random variable defined in example 4.19. So we want to find expected value of y, which is 1 over 4 times expected value of x1, which is 0, plus 3 over 4 times expected value of x2, which is 1. So this is 3 over 4. And what about variance? To get the variance, we can first we calculate expected value of y squared, and this is again 1 over 4 times 0 and plus 3 over 4 times expected value of x2 squared, which is 2. And so this is 6 over 4, which is 3 over 2. Okay, and now we can calculate variance of y, which is e of y squared minus ey squared, which is 3 over 2 minus 9, 16, and you can calculate by yourself. Okay, so we calculate mean and variance. Okay. Homework for chapter 4.11 is this one. And homework for supplementary exercise problems are these. Okay, so far we have learned about continuous random variables and their probability distribution functions. So from next chapter, we will learn about multiple distribution function for multivariables. Okay, see you next class.